Jacob, please start.
Thanks, Yoko. So we're securing over 2 billion connections. We've done over 15 years securing automotive designs. Most of this webinar will be about some of our automotive projects, and we'll get into detail about a couple of the automotive projects that we've done previously. So there are 3 main areas that wolfSSL focuses on. All of these areas are dealing with securing your data, and they're relevant in the automotive industry. The first being data in transit. This is done with protocols like TLS and SSH. They allow for data integrity, authentication, and encryption when sending and receiving information. The second area that we have focuses on data at rest. We have our crypto library that supports progressive ciphers, as well as the well-known standard algorithms, such as AES. This can be used to encrypt data at rest. The third focus is providing software that assists with firmware updates, this being our MQTT implementation, or through use of TLS also. Having a secure mechanism for firmware updates helps reduce the risk of malicious firmware being introduced. Many of our products that are offered are used in the automotive industry. A lot of automotive projects have involved wolfSSL use, which is our flagship TLS implementation, making use of the tried and true wolfcrypt library for its crypto operations. Other projects that we have done for automotive companies involved wolfSSH being used on test rigs and firmware updates. wolfSSH was also used in a case where you could log in and be able to see test data, such as the output from standard air being piped to a terminal. One of our latest software products is Sentry. It is a nice fit into embedded use cases for intrusion detection and prevention in the automotive space. We also have the Swiss Army knife of URL tools, which is curl. It's another product that sees frequent use in the automotive industry, and it's in basically every infotainment system used. We have support packages that we offer for use with curl, and a recent tiny curl build for a slimmed down version that can fit in more restrictive, resource-constrained devices. Wolf Engine is provided as a solution to FIPS certification. So if using OpenSSL, for example, and looking for a quick FIPS certification process, you can use Wolf Engine. And later on in the presentation, I will be going through some of the specifics about how these products were used in the particular projects. All of them, like wolfSSL, for example, has been used on a lot of the popular automotive operating systems. wolfSSL has been ported to QNX. We've used it with AutoZar, Integrity, which is the Green Hills Integrity OS. We've used it with VxWorks, FreeRTOS, automotive grade Linux, and wolfSSL can even be used on bare metal devices. So it can be used in like a microcontroller kind of situation. So wolfSSL has a long history with use in automotive systems. The company has 15 plus years of experience working with and developing for automotive companies. One of the first companies we worked with was General Motors, and since then have expanded to be in 3 out of the top 5 auto vendors, with major customers in Japan, Germany, USA, and France, to name a few of the places. wolfSSL products are used in a broad range of applications in the automotive industry, anywhere from ECUs to telematics to infotainment systems. And with the reliability and support that we provide, two of the world's biggest auto vendors have standardized on us. So as the automotive industry advances, more communication between devices in the vehicle is introduced. In the simple old school vehicles, communication between components was all mechanical for the most part. Now with more efficient and sophisticated functionality that is coming about in current vehicles, the communication between the components has changed to be more complicated and electronic to handle the increased bandwidth. Some of these components being communicated with are system critical, such as, for example, the brakes and the steering are both system critical components that you don't want to have be tampered with. So it's important now more than ever to have security with the intercommunication system as well as with the external communications with the vehicle. And when you think of electronics and communications in systems in a vehicle, usually the first thing that comes to mind is, at least for me, is luxury vehicles. And I'd like to point out that in the automotive industry, we're not constrained to just luxury vehicles. wolfSSL products are used in military vehicles. We're also used in agricultural and heavy equipment vehicles. This could be anywhere from like a swather connecting back to a GPS connection, for example. Heavy duty and lightweight trucks. This is anywhere from semi trucks to small pickup trucks. Semi trucks being the fleet communicating back and forth when they're going to apply the brakes if they're drafting off of each other. Or small pickup trucks being the mobile, basically the mobile offices that construction crews have at the moment. In both the vehicle and the back-end servers that may be supporting the vehicle operations. And when I say back-end servers, I'm talking about things like OnStar connections, for example, where it communicates back to some server. That server could also be using wolfSSL. Okay, so the first project I'll be talking a little more about in detail that wolfSSL did with the automotive industry was a vehicle-to-vehicle use case. With the increase in car connectivity, it becomes useful for vehicles to share information with each other. This can be helpful in many ways, but not everyone the vehicle connects to may have good intentions. Solving this issue requires authentication of who's been connected to, but it also requires that authentication to happen quickly in order to not diminish the user experience and to keep up with how fast things are happening on the road. In this particular project for vehicle-to-vehicle use, we leveraged the DSP, which stands for Digital Signal Processor, to get the most that we could out of the hardware that was being used. This helped in multiple ways. One of them being that the crypto operations could then be offloaded, freeing up the main CPU for other operations. It also helped in high volume cases by being able to run more verification operations in parallel. So if it was to get in a high volume traffic kind of situation, be able to handle up to the 16,000 verifications per second needed. The main crypto library, wolfcrypt, was used for signature verification. And to help with the performance requirements, it was built with SP math. SP stands for single precision. It's a single precision implementation that my coworker Sean developed for commonly used key sizes with some asymmetric key algorithms. And the SP math was extended to be used on the DSPs available, along with potential caching for performance enhancements when verifying using the same key multiple times in a row. Another part of the use case was a custom library built for dispatching verification operations. The code assisted by handling receiving a verification request and directing which processor the verification should be done on. For this case, we also implemented SM2 in order to be used in the Chinese market. This implementation is not in our main branch or release bundle, but it is something that we have available if needed in a project. So one of the big hurdles for engineering on this use case was the communication between the cores. So passing cached information for performance enhancement from one core to the next that would then do the verification operation. the data has to be either serialized in a generic way, or either the code on both cores compiled to expect the same size of data types. In this particular project, we went towards the later, having the code compiled to expect the same size of data types so that we could pass information back and forth faster, not having to deal with any kind of serialization of it, generic serialization of it before passing it to the other cores. The project called for a lot of optimizations and performance enhancements. One performance enhancement, for example, was adding Brainpool and SM2 support to the SP map. Another investigation was done to potentially leverage the HVX, which handles operations with large vectors very quickly. And throughout the development, many benchmark collections were made to investigate the trade-off of the number of threads being ran in parallelism versus the point where tasks switching between the threads affected the performance negatively. We also did a lot of isolation testing, basically testing of the dispatcher code that it would pass the verify requests reliably off to a single core, and then that core would be heavily used while all the other cores were not. So we went through quite a few tests to make sure that it could isolate the work. So the next project that I'll be talking a little bit about was a secure firmware update. In this particular use case, we were used for retrieving and authenticating a new firmware update. It phoned back to a backend server using wolfSSL plus curl. And we built it in such a way that it had leveraged the CAM on an IMX device. CAM is the crypto assurance and acceleration module that NXP has. It helps will speed up the crypto operations, offload it from the CPU, and then it also helps with heightened security. So the products, that we used in this particular project was curl, which made use of wolfSSL, and underneath that it used wolfcrypt for the crypto operations, and then tied into the CAM hardware. We implemented a QNX driver to be able to communicate between wolfcrypt and the CAM hardware for this particular project. So it leveraged some of the specific engineering detail about it is it leveraged the IMX6 device and vastly improved security by using the CAM. We made use of black encrypted keys. Black encrypted keys is a method of using the key encryption key on the IMX6 device to encrypt the key, the ECC key, when it's created. This encryption happens in hardware. So before the key ever reaches any memory spaces where it could potentially be read, it's already been encrypted. And then once it's going to be used again, that encrypted version of the key is passed back to hardware, decrypted inside the hardware, and then used. So the plain text version of the key is never in a memory space that it could potentially be read by a malicious entity. And this was done both during just like a ECC key generation and verify and sign. It's also used with the ECC ephemeral keys during a TLS connection. And one of the additional features that we added in this particular project was red and black blobs. Red is the blobs in general with the NXP is kind of their scheme to be able to store data securely through a power cycle. If you were to take that previously mentioned black encrypted key, save it to memory, then do a power cycle and try and use it without first storing it in a black blob, it would no longer be usable because the hardware would no longer be able to decrypt it. So these black and red blobs is a way to be able to store information through a power cycle. Obviously, the black version of them is for the black encrypted keys. The red version of them is for any text coming in. And this was running with QNX, specifically QNX 7.0 to begin with. Near the later ending of the stage of the project, it was QNX 7.1. So it was the latest QNX version at the time. And we wrote a driver to be able to communicate in between the wolfcrypt library and the hardware. So performance of sign and verify with black encrypted keys is close to an optimized unencrypted operation. And down at the bottom of the slide, I show some of the performance comparisons. As you can see, the software only averages were a lot slower than both the QNX and the SP ASM versions. The thing that was interesting is the QNX encrypted black keys was close, if not faster, than the assembly versions that were optimized for the particular ECC operation. So you can see the key generation is slightly slower, which you would expect because the black keys, it's doing encryption of the key when it generates it. And to specify that it was the AES CCM version. So not just they have two versions of black encrypted keys. They have the AES ECB and the AES CCM. So this is a AES CCM encryption, which also has the MAC at the end. And the agree was actually faster. So with the ECC 256 agree, the QNX CAM black keys averaged faster than our SP assembly version. And you can see the other results on the bottom there, the sign, verify, and encryption. So another project that wolfSSL is used in for automotive use is with a TLS connection from the car to the backend server. This includes the option of using the most recent TLS protocol, TLS 1.3. There's a relatively complex network setup involving both wolfSSL's TLS and MQTT implementations. For those that may not know, MQTT is a publisher subscriber protocol, which can be used for mass updates or just for sending info to many subscribers at once on a network, with varying times of when the device is connecting or reconnecting. An example of a potential use case for Wolf MQTT could be used with sending road conditions to all subscribers in a specific city or weather updates to a specific location of subscribers. The device would communicate through this secure connection using a proxy setup with the backend server in this project. The main wolfSSL products used in the project were wolfSSL, Wolf MQTT, and curl. Curl is commonly used in a lot of these automotive projects, and it's combined with other wolfSSL products, such as wolfSSL in this case. Daniel Steinberg, the author of curl, he works with wolfSSL, and we have support packages and consulting offered, which helps streamline the experience of integrating the libraries into an automotive application. No major consulting was done with the project. Most of the engineering efforts were around supporting and integrating and assisting with resolving any issues that came up. With Wolf MQTT, the project was using the V5 implementation, and it also used some additions that we did for multi-threading. For use in the project multi-threading with Wolf MQTT, it was expanded upon. A lot of the questions that we resolved and technical efforts that we did in this project were related to expansions and more robustness to our MQTT library. Another one that wolfSSL has been used with is autonomous driving software. The automotive industry has been progressing towards fully autonomous vehicles, and the need for security with communications and critical system operations when a heavy vehicle is controlling itself down the highway is paramount. And the software application wolfSSL was used for connection to the server for map updates. The connection to the server for map updates assisted with navigation. This up-to-date map setup for navigating through roadways was used in an advanced version of cruise control that assisted not only with maintaining speed, but also with maintaining position on the road. And the wolfSSL products used in this setup were the main wolfSSL library with TLS 1.3. So that's the most recent TLS protocol. We were one of the first to commercially have it available. And this was also used with one of the many automotive OSs that we support. It was a Green Hills port. And for security reasons and to fulfill the industry requirements, many of the projects we work with are using either QNX or Green Hills for the operating system. And we fully support both along with other potential operating environments that may be used. And we also support, as I mentioned earlier, bare metal, which can be used on the microcontrollers as well. A few of the engineering specific details about this project was the porting work done to run on a ST Telemaco board. Porting to new systems often requires setting up the hardware source of entropy if available, handling any mutex uses, if using a multi-threaded build, setting the types correctly for the hardware among other small modifications. wolfSSL is set up in such a way so that it's very modular, very portable. All of the system calls and locations in code that need to be ported are abstracted away, but it usually goes quicker when having a wolfSSL engineer doing this port for you. In this particular case, we were hired to do that port for them. Okay, so there's also some hardware acceleration that was done. It made use of the A7 core, so it could use some of our existing assembly accelerations that we have for the A7, but it also had some more specific hardware crypto acceleration that the board supported. So we had some tie-ins that we did for that. We did some MISRA-C work on this project as well. It was done with some specific wolfcrypt files. We find that a lot of automotive projects require static analysis reports to meet their standards. But to be compliant with these requirements, it's just a static analysis report, not necessarily a MISRA-C. So most of the times when MISRA-C is brought up, it turns out to not be a requirement in the end, just the static analysis report. Another automotive specific use case that we support is NTP for AUTOSAR, so Network Time Protocol. Time stamping events for smart cars it's often overlooked, but a very important element. So the ecosystem time sync examples of why the time sync and timestamp is important is such as brakes having the same time reference as machine vision systems. So if you have some advanced cruise control that detects an obstacle in front of the vehicle, you want it to send the correct time for when the brakes should be applied, rather than too late or too soon. Both too late or too soon could end up disastrous. And it's the NTP that we did was maintaining a constant sub-millisecond time in a vehicle. So it has to be not only accurate, but it has to be within a certain time slice, which was a sub-millisecond in this particular case. And it was cryptographically secure reference of time. So it was more resistant to being tampered with, which also is pretty critical, especially with elements that need to be secured to be safe, such as the brakes, as mentioned before. So why do we need NTP in a car? Besides the example mentioned earlier about the brakes, we also need the sync of subsystems and smart car apps. So it can be quality of life, for example, not just necessarily all of the safety critical elements. If you have a device that is connecting to the car, such as your phone, it's nice for the time syncs to be accurate. And then also for forensic reconstruction of events. So in the case that if a crash did happen, you'd want the events leading up to the crash to be in order of how they actually happened. So one of the more recent products that we had gotten here at wolfSSL was the Sentry. And this is how Sentry fits into the automotive industry. Sentry is at its heart a firewall, but it can also be much more than a firewall. It has the ability for rules to be added in. So not only can it passively monitor and block, but it can follow particular rules that are set to be able to react to events. So it can dynamically respond to block bus spam, for example. And we have examples of these setups through like our wolfSSL project and LWIP. Those are just a couple of examples that we have in particular at the moment. We're also doing like wolfSSH example of the tie-in for Sentry. But it's built in such a way that it's lightweight. So it's good for resource constrained devices, and it can be a good match for running on embedded devices to be able to detect and block things like spam bus. One of the industry standards out there in the automotive industry is the ISO 21434. Sentry IDS helps with meeting this standard. It's designed for embedded devices, has the dynamic rule generation and transactional rule changes on the fly. And it's able to record or react to events. Then wolfSSL also helps with meeting the standards by securing transmission of the event data. It can secure general communications between microcontrollers and servers. One of the other products that we have is the wolfBoot, which is a allows for secure firmware updates. Recently, one of my coworkers did TLS over CAN. So CAN stands for the Controller Area Network. TLS, it allows for ability to authenticate, encrypt, and also check integrity. CAN is used for the top industry standard for intra-car communication. So this would be more like security for physical attacks. If someone was physically close to the vehicle and able to insert a device onto the vehicle itself. CAN is often overlooked as far as any security being done on CAN. And a little bit about how we implemented this in practice. Those familiar with the CAN bus, you know that it only has a 8-byte max packet size, so it's tiny packets that are being sent across it. And that doesn't have much space, let alone doesn't have much space for TLS, let alone for TCP connections. TLS can be up to a 16K packet size. So to be able to work around that, we use the ISO-TP wrapper with variable minimum packet delay. This allowed for TLS to be ran across it. It's also adaptable for the CAN FD. And we use TLS 1.3 with this implementation. The reasoning behind that was TLS 1.3 has reduced round trip handshakes. So that cut down on the number of packets that needed to be sent back and forth. It also has a simple callback interface, and it's platform agnostic CAN bus wrapper. So it can be used and not only with the automotive with the gasoline can, but also with like the diesel. So they have two different variants for it. We do a lot of testing here at wolfSSL. We have one of the best tested one of the best tested crypto libraries. And we do this testing in order to avoid crashes. In this particular case is software crashes along with automotive crashes. We want to avoid both of them. Testing and code quality, some of the things that we do is we have benchmark tests on real hardware, multiple boards. So we keep track of code size versus boot time, measure memory resources, manually run additional resource collection to update usage figures. We have functional tests running on a real STM32 F407 target in Amsterdam. So my coworker who did a lot of work with the Wolf boot is over in Amsterdam, and he has that STM32 F407 continuously running with covering forward update and rollback tests, SPI flash tests, TPM tests, using the Infineon TPM module, and testing with combination of a possible DSA plus SHA algorithms. And this is just a small section of the testing that we do related to like the automotive industry. We have quite the test rig that operates here in the Bozeman office where I am. So this is a rainbow of testing, as we call it. What we have is the core testing with the API tests and unit tests. So that's part of the core of our testing. And after that, it's peer reviews. So all of the code before it gets merged into our master branch, it gets reviewed by one of our senior engineers. And we have static analysis tests that are continuously running. We have memory leak check tests that are continuously running. We use the well-known Valgrind. We also use Infer, and to name a few of the memory leak checks that we use. We have interoperability testing that's done before each release, Cypher suites, certificates testing, regression testing, many builds and options that are tested. We have product testing, so we have the FIPS version of the code that gets tested along with any new code that gets into wolfSSL, and the SSH library gets tested with any new code, for example, and then JNI MQTT, to name a couple of our other products that get tested with it. And we have testing on multiple OSs, testing with our hardware acceleration, different compilers. Then we have fuzz testing that we do, third-party testing. So third-party testing involves other universities. We have our open source community that's testing it, along with a couple of third parties that we hire as well for additional testing. Benchmark testing, our wrappers, C#, JNI, Python wrappers, which get tested upon each release. And then on the outer layer of our rainbow of testing is the new tests that we're constantly adding. So at that point, I think I covered the basics of some of the automotive projects that we've been used in, and I'm going to go ahead and open it up for if there's any questions.